We're in section 1.3 of Rosen, Discrete Mathematics and its Applications, and we are talking about propositional equivalences. Here are the topics covered in this section. We will cover the first bullet, and under the second bullet we'll cover important logical equivalences, which we will also call identities. First, some definitions. A tautology is a proposition which is always true. Here's an example. P or not P. Remember, in the disjunction, if either argument is true, then the compound proposition is true. And with P or not P, one of them is always true. A contradiction is a proposition which is always false. And the example here is P and not P. Since one of P and not P is always false, and the conjunction requires both to be true, then this compound proposition is always false. And a contingency is a proposition whose truth value depends on the value of the atomic propositions. One example, a very simple one, would be P itself. The value of P depends, obviously, on its truth values. So here's a truth table that illustrates these points. P is contingent on its value, but P or not P, as well as P and not P, are not contingent on the value of P. They are tautologies and contradictions, respectively. Okay, so we use the concept of a tautology to define logical equivalence of two propositions. We say that two compound propositions, we'll call them P and Q, are logically equivalent if P, if and only if Q, is always true. Remember, if P, if and only if Q is always true, that means P and Q always have the same truth value. And when they always have the same truth value, that means they are logically equivalent. There's a couple of ways that we can symbolize this, but the more common way is to use this triple equal. To say that P and Q are logically equivalent would be P triple equal Q. And then again, the way we can test this is using a truth table to see if their values always agree for all the input values of the atomic propositions. We're going to show that the compound proposition, the negation of P or Q, is equivalent to P implies Q. So since this has two atomic propositions, our truth table will have 4 rows. And here's all the possible values of P and Q. And we remember from the definition of implication that P implies Q has the truth value sequence of true, false, true, true, given our typical settings of P and Q by row. But notice that if we evaluate not P or Q, we get exactly the same truth values. And so these two, we just have proven that these two compound propositions are logically equivalent. And if we were to set up a table that said the fourth column and the fifth column in biconditional with one another, it would be a column of truths. So that would be the tautology. Oh, and by the way, so this is what we would call, this is our first identity. P implies Q. We can replace with not P or Q, and vice versa. A couple of more important identities are called De Morgan's laws, and I'll just read them. The negation of P or Q is the same as the negation of P, the negation of P and Q is the same as the negation of P or the negation of Q. In other words, if it is not the case that P and Q are true, that means one of them must be false. And then the negation of P or Q is the same as the negation of P and the negation of Q. In other words, if it is not the case that P or Q is true, that means they both must be false. And we can use a truth table to prove these results as well. So again, it's going to be a 4-row truth table. And if we can work across and we'll see that the negation of P or Q has this truth value sequence. And the negation of P and the negation of Q has this same truth value sequence. And so we have proven De Morgan's second law with a truth table. There are many other identities that you'll want to be mindful of, and I'll just run through them quickly. P or true, excuse me, P and true is always the value of P. P or false is always the value of P. You can prove this using a truth table. Domination laws. So we use these names when we're doing proofs. So the identity laws is what we just covered. Now the domination laws. P or true is always true because one of the two arguments of the disjunction is true. And P and false is always false. In other words, true dominates the first of those two and false dominates the second of those two. Idempotent laws. In this case, when we have a duplicate entry in the disjunction or the conjunction, we get that atomic proposition out by itself. So P or P is equivalent to P, and P and P is equivalent to P. Double negation, as you might expect, the negation of P is logically equivalent to P. And then what we call negation laws is what we saw on the very first slide. P or not P is true, and P and not P is false. All right, a couple more slides on key equivalences. Commutative laws. P or Q is the same as Q or P, and P and Q is the same as Q and P. Associative laws. In this case, if we have a string of disjunctions or a string of conjunctions, it doesn't really matter which order we do them in, you get the same result. And you can prove this with the truth table. But if we have P and Q and R, if we do P and Q first, and then R, it's the same as doing Q and R first and then P. And then distributive laws. If you have a disjunction over a conjunction, you end up getting, you could imagine that you're distributing this into here and maintaining this conjunction. You end up getting a conjunction of two disjunctions. And similarly for a conjunction over a disjunction, we are distributing it inside of here so that we get a disjunction of conjunctions. And then finally, the absorption laws. P or Q and P gives us P, and P and Q or P also gives us P. And I encourage you to prove these to yourself using truth tables. And finally, some very important identities or logical equivalences listed here. This top one is the one we saw earlier. P implies Q is the same as not P or Q. This next one is the contrapositive. So P implies Q is the same as not Q implies not P. And a lot of these others will be very similar applications of these prior equivalences. And you can prove each one of these using a truth table, and I encourage you to do that. Over on the right, we have some logical equivalences involving the biconditional, and these are all very important. P if and only if Q can be thought of as P implies Q and Q implies P. So one of the ways we'll do proofs of biconditionals is by doing two different proofs using implication. And then P if and only if Q is the same as Q, P and Q, or not P and not Q, meaning that P and Q both have to have the same truth value. And that is our discussion of key logical equivalences.